Remember in our last video how Stella fell into a 20 million solar mass black hole from an initial position of R0 equals 10 GM, and we calculated that she oscillates back and forth with a period of about 2 hours according to her watch? Well, in this video, we will see what happens to Stella according to Tom, who's back on Earth. We begin once again with the Schwarzschild metric, whose d theta and d phi terms have been cancelled, since Stella moves only in the radial direction. But unlike what we did in our last video, this time we divide through by dt squared, Tom's faraway time interval squared, rather than d tau squared, Stella's proper time interval squared. Now let's take the geodesic equation, invert it, square it, and substitute it into the Schwarzschild metric. Now let's manipulate and multiply through by 1 minus 2 gm over r. Now let's factor out a 1 minus 2 gm over r squared from the left-hand side. Now let's find a common denominator inside the curly brackets and simplify further. And now let's bring the dt squared over to one side, and all the terms involving r to the other side. Okay, let's manipulate what's inside the curly brackets a little bit. Now let's take the square root of both sides. The integral on the left is trivial, whereas the integral on the right is trickier. In order to perform this integral, let's make the substitution that x equals the square root of r0 over r minus 1. Then dx equals 1/2 over the square root of r0 over r minus 1 times the derivative of the inside, which is negative r0 over r squared dr. Manipulating this equation a bit, we see that dr over the square root of r0 over r minus 1 is equal to 2 times negative r squared over r0 dx. Let's now substitute this equation back into the original equation. Let's put the fraction in the numerator into the denominator. Now let's multiply both sides of the equation by 1 over r0. Since x is proportional to r0 over r, let's multiply the numerator and denominator on the right by r0 over 2 gm in order to create an r0 over r term in the denominator. And let's move the constants in the numerator over to the other side. We see that r0 over r is just x squared plus 1, so we can now make that substitution into the equation. The second factor in the denominator is the difference of squares, and it can be factored into the square root of r0 over 2 gm minus 1 minus x times the square root of r0 over 2 gm minus 1 plus x. To find the integral, let's use the method of partial fractions and write out the integrand as a over x squared plus 1 plus b over x squared plus 1 squared plus c over the square root of r0 over 2 gm minus 1 minus x plus d over the square root of r0 over 2 gm minus 1 plus x, where a, b, c, and d are constants to be determined. To discover the value of these four constants, let's multiply the equation through by the entire denominator, namely x squared plus 1 squared times the square root of r0 over 2 gm minus 1 minus x times the square root of r0 over 2 gm minus 1 plus x. In that case, the denominator completely clears from the left-hand side, and on the right we are left with the sum of the four unknown constants multiplied by whatever factors were not underneath them to begin with. This equation must be true for all values of x, so we can set x to some convenient values to help us determine the four constants. If we set x to the square root of r0 over 2 gm minus 1, Only the c term remains on the right-hand side of the equation, and it can be determined after a few simple manipulations. Let's now go back to the original equation for a, b, c, and d. This time let's set x equal to negative the square root of r0 over 2gm minus 1. Now the only surviving term is the d term, and with some manipulation we can solve for the constant d. It turns out that the d term and the c term have exactly the same value. Let's back up once again to the equation that's helping us find out the constants a, b, c, and d. We still have a and b left to solve for. To find b, let's just set x squared equal to negative 1. Don't worry, it's okay to set x equal to an imaginary number. Then all terms vanish except the b term, and with a little manipulation we can solve for b. Alright, let's bring back that equation for the four constants a, b, c, and d one last time. In order to find the value of a, the best thing we can do is set x equal to 0. So let's do that. Now let's substitute in the values for b, c, and d. Now let's simplify. Now let's factor out 2gm over r0 from the left-hand side. Now let's multiply both sides of the equation by 2gm over r0. The right-hand side simplifies to a times 1 minus 2gm over r0, so the 1 minus 2gm over r0 on both sides of the equation cancel, and we are left with a equaling 2gm over r0 squared. So we can replace the integrand on the right-hand side of the original equation with these fractions. Let's simplify the left-hand side of the equation by taking a gm squared out of the square root, and then dividing the numerator and denominator of the square root by 2gm. Now let's move the constants that multiply the t over to the other side. In the numerators, some cancellations occur. The first integral we recognize immediately as inverse tan x. The next integral is not so easy to recognize, so let's make the substitution that x equals tan theta. Then dx is equal to secant squared theta d theta. Recognizing that tan squared plus 1 is equal to secant squared, we can make that substitution. One of the secant squareds cancel, and we can write the remaining secant squared as a cos squared up in the numerator. Now, remembering our trig identities, let's write cos squared theta as 1/2 cos 2 theta plus 1 in order to more easily integrate it. Let's bring the 1/2 out of the integral. Okay, now we are ready to integrate. The integral of cos 2 theta is 1/2 sine 2 theta, and the integral of 1 is theta. Now we should write the integral in terms of x rather than theta. We immediately see that theta equals the inverse tan of x, so we can make that substitution right away. To find out what 1/2 sine 2 theta is in terms of x, let's write tan theta as sine theta over cos theta, and then cos theta as the square root of 1 minus sine squared theta. And now let's manipulate this equation in order to solve for sine theta. Now let's write sine 2 theta as 2 sine theta cos theta. The 2's cancel, and now let's write cos theta as the square root of 1 minus sine squared theta. Now we're ready to replace the sine thetas in the equation with x. The terms inside the big square root can simplify. We've now finished the integral, and we can insert it back into the original equation for t. And the integral of the last two terms are nothing but natural logarithms. After factoring out a 2gm, the logarithm terms can be combined into a single logarithm term. Now it's finally time to replace x with the square root of r0 over r minus 1. And now let's clean things up a little bit. This is our final expression for Bob's faraway time t as a function of Stella's Schwarzschild radius r. Alright, this is exciting. Let's set r equal to 0 and find out how long it takes for Stella to reach the singularity. Looking at the first term, the argument of the inverse tan function is infinity, and the inverse tan of infinity is pi by 2 plus pi times an integer. The second term is 0 by inspection, and the last term is also 0 for the following reason. In the limit as r approaches 0, the second term in the numerator and the second term in the denominator dominate the expression. The first terms are insignificant. Therefore, the numerator and denominator approach equality as r approaches 0, so the expression inside the logarithm approaches unity as r approaches 0. The logarithm of 1 is, of course, 0. Let's put in Stella's initial position of r0 equals 10 gm and calculate her infall time. Now the g in this equation is just Newton's constant of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And recall that the mass of the black hole that Stella is falling into is 20 million solar masses. Multiplying the numbers together, we find that minus or plus t equals approximately 1.17 times 10 to the 29 Newton meters squared per kilogram, multiplied by 1 plus 2n, where n is an integer. To convert these units into seconds, we write a Newton as a kilogram meter per second squared. The surviving units are meters cubed over seconds squared, so it's clear we must divide by the speed of light cubed in order to obtain our final units of seconds. This, roughly speaking, is 1 hour and 12 minutes. The minus and plus sign in front of the t0 is redundant at this point because n is an integer and can take care of all negative as well as positive numbers for time. So we can get rid of that minus and plus sign for this calculation. So the picture from Tom's point of view may look like this. Stella oscillates back and forth from r0 to the center of the black hole, back to r0, then back to the center of the black hole, then back to r0, with a period of approximately 4 hours and 48 minutes. Notice that n equaling 0, 1, 2, 3, etc. corresponds to Stella revisiting the center of the black hole during each oscillation. As you may recall from our previous video, this is not very different from the 4-hour period timed by Stella herself. Is this really true, that Stella just oscillates back and forth, and she and Tom agree on the passage of time within 48 minutes or so per oscillation, assuming, of course, Stella doesn't interact with the singularity within the black hole? In order to shed some light on the answer to this question, we must look more closely at Tom's far-away time as a function of Stella's Schwarzschild radius r, and we will do that in our next video. Thank you for watching.